All right, everybody, welcome to Earth Science. So let's picture this. You have a very dirty Oswego County car, which is typical, right? They put sand all over the roads here, which is better for water quality, but not so good for the way the outside of your car looks, right? So it's filthy, and let's pretend it's nice out today and sunny and warm. We go to spray it down with a hose, but man, that stuff's really in there. It's not moving. So what else do you do to your hose to get it going? You know, the little trick where you put your thumb over the end and the water goes faster, and then you realize that that faster water does a better job of cleaning off the car. Or somebody earlier said pressure washer. That'll really do it. And the water's really going faster, and you'll get all that sediment off your car. Now, that's like a common thing, right? What you've probably never said, if you've ever done that, is I'm going to go outside and erode some sediment off the outside of my car. But it really is what you're doing. Think of that as erosion. You're moving sediment. We've already said that's what erosion is. So, like, that's really just an erosion experiment you're doing, whether you do it or not. You realized that when water speeds up, and you do that by holding your thumb over the end of the hose to make the hole smaller, to make it go faster, the rate and amount of erosion, this really should say increases, but that's okay. Um, so what we got, like that, I think that is usually pretty intuitive. People make sense out of that. Like you know that the faster water is going to move sand better, right? Well, we're going to do that mathematically now using this table right here, which has a very complicated name. The relationship of transported particle size to water velocity. That's a mouthful, especially with like vocab. So let's make the title of this a lot simpler. Here's the title of this. This table shows us how fast does water have to go to move certain size sediments, right? Just like we set up here. You make the water go faster, it moves these sediments. How can we mathematically relate how fast really does that water need to go to move what size particles, right? If I took some like fish gravel, you know, that like fine stuff you put in fish tanks, and went down to the Salmon River in spring, like when it's raging after a rainstorm, and chucked it in, is that river going to be able to move those little particles? Probably. It's probably going fast enough to push those downstream a bit. If I went and dropped a boulder the size of like this, you know, this lab bench right in the middle of the river, water's not going to do anything to it. So how fast does the water have to be going to move the different size particles? That's what this table solves for us. And it is, we should make a note of this, available to you any time of day or night because it is ESRT. Sorry, disappeared. ESRT, page 6. Okay, so expect Regents questions on it, expect to use it. So let's learn. How do you do it? Let's talk about a couple valuable things here. First, see these 6 things right here? I was having everybody in class circle them. I think it's a good idea. These are the official particle sizes, defined strictly by these sizes. So everything between 0.0004 centimeters and 0.006 centimeters is called silt. Silt is defined as that. Clay. Sometimes people don't think of clay as a particle size, but it's a very, very, very fine particle size. And I know, yes, you can, if it's pure clay, you can mush it and mold it and then put it in a kiln and it turns hard. But that's what it is. It's little tiny sediments, less than 0.0004 centimeters, teeny tiny, right? Bigger than that, clay to silt to sand to pebbles to cobbles to boulders. This does not say what a cobble might be made out of. It could be like the bricks I have in the back of the classroom, though those are man-made, probably not. But it could be sandstone, granite. It could be anything, right? All this talks about is the size. Anything that's this size from 6.4 to 25.6 is defined as a cobble. And that's not just like a me thing or even a New York thing. This is a real deal. That's how it works. Okay. That said, here's the job. This black line is the answer to the questions. This black line tells you how fast the water has to be going to move the size particle, right? Stream velocity, speed of the water, particle diameter, size of the bit, right? So let's do the first one, and then a hell of you try some of the other ones. If the stream velocity is going 1, so my stream velocity is moving 1 centimeter per second. There it is right there. We'll blow this up a little bit. A little bit more. the stream velocity is going 1, all I'm going to do is follow it up to this black line, because again, this black line is the answer to all of the questions. That's where it hits. That's where the answers lie. My particle diameter is that, and the name of that size particle is sand. Okay. Now, yes, these like lines look a little crazy. They're not linear. We had this also happen on the star one, their HR diagram. If you remember that, they're nonlinear axes. They're logarithmic. Don't let this panic you though. You can figure it out as long as you have the right number of zeros. Estimations are usually going to be good enough. And again, they do that. Like, look, it goes from 1 to 5 to 10, then 10 to 50 to 100, then 100 to 500 to 1,000. They do that again to not have the graph like be the width of the room. We got to compress down all of that into a reasonable amount of space. So they make these kind of funky looking, kind of intimidating, but don't worry, you'll figure it out. Kind of graphs, kind of axes. All that said, at 1, I'd say the particle diameter here, if that's 0.01, that's 0.02. So we'll check that right in there. The name of that particle, as we said, is sand. There you go. Now, if you're doing this from home, I do appreciate it. We did do this in class. But the only way that you're going to be able to figure some of these out is if you practice. So I think the best bet for you right now is to press pause and do the rest of this data table right over here. Do that now. Do that, and I'll come back and check a couple. Go. Press pause. I will too. All right, did you do them? I'm probably not going to do all of them so that this video doesn't end up being like super long. Let's do one or two, make sure we're on the right track though. 0.001 as a particle diameter. 0.001 is right there. So again, the answer lies on this line. Where does it meet that? The name of that particle, that part's easy enough. Should be silt. And then the velocity, how fast does the water have to be going to move silt? Silt's pretty tiny, so not so fast. If we come down from there, looks like it hits right about there at 0.05 centimeters per second. That's going pretty slow. Okay, that's going to be the idea on these things. That's how you do it. The cobble one, hey, that could be anywhere greater than 6.4 and less than 25.6. So what answer did you pick? Maybe, I mean, I just think it's easiest to just do the one that's printed there just to make my life easy, your life easy. So let's do 10. Right, a cobble, yes, could be 10 centimeters. And then how fast would the water have to be going to move that? If we come right down from there, it's in the ballpark of 200. Don't get too panicked about like lining everything up just right. Usually Regents questions give you a little bit of flexibility and you're going to be okay. All right. Let's talk relationships. And again, I hope you did those 3. I just don't want to take too much time on this. And you'll have other opportunities to check some. What is a relationship? As soon as you hear that word, we're not quite to 100% of everybody nailing these yet. Relationship questions in earth science are pervasive. They're always going to be there. What they want to have us do is compare, not really compare, like say how does one thing affect the other? So as soon as you see the words, what is the relationship? The first word that should tumble into your mind as an answer, go with as. And then your job is just to say, what are the 2 things that they're asking me to see how they affect each other? How does stream velocity affect that particle size transported? I mean, after all, that's even the title of this. This graph is exactly that, right? So what is this graph showing us? What is it showing us that happens here in real life on your planet? So relationship questions always answer the first thing. Yeah, stream velocity. Now you can either choose increases or decreases, whatever you want. You can answer it the same. You can answer it equally validly either way. I'm going to go increases. As stream velocity increases, what does that do? What is my brain telling me that does to the size of the particle that can be transported? The faster that water, with this line, it looks like I'm going to larger and larger and larger particles. So the particle size transported also increases. Excellent. All right, try these three. Um, Press pause and try these three because these are also going to reveal. In fact, if you want to do this, do this one first. I know this is a weird order. I should just fix it, right? Do this one first, this one second, and this one third. All right, press pause. Do those three now. Won't take long. Pause, pause, pause. All right, you're back. This one I think is the easiest. The minimum stream velocity to transport a sediment particle that is zero point 0.1 centimeters. So 0.1 centimeters, we're right here. I need that spot. And they're looking for a speed. I come down here. It's somewhere in the ballpark of 5, which you can see that the regions tends not to get too make the answers too close together. Sometimes a little bit, but this one very clearly, there's nothing even close to 5.5. So I'm pretty comfortable saying that. Let's go over to this one. Which particles will be transported by a stream moving at a velocity of 5? So if my it's going to be similar, huh? How about that? All three questions use about the same answer. So if we're going about 5, we come up to here, we can see that I can carry most sand. So here's an idea, though. If I can carry sand, can I carry pebbles? No, because the pebbles are too big. But if I can carry sand, can I carry silt? Yes. You can really carry that and everything smaller with that speed of moving water. So what will be transported by one that's going 5? It'll be this: sand, silt, and clay. Which now gets to the idea which we're going to get into when we get into the river thing here. This is the big one. Um, what if you're going 50 and then it decreases to 5? All right, so if we're going 50, we can carry, and I know that line's not super straight, but we're going to be good enough. We can carry pebbles and sand and silt and clay. And then if the water slows down to 5, something happens. Now it can only carry the sand. So what happens to those pebbles? And this is getting into, like, remember, this whole unit is weathering, erosion, and deposition. So what happens to those pebbles? They can't be carried anymore. They're going to fall out of the river. They're going to drop to the bottom of the river, which is what deposition is. It's the drop off of sediments. So the answer here, cobbles were never in play because the water was never fast enough to carry them. The particles deposited would be these: the small pebbles and large sands that were being carried at 50, but can no longer be carried at 5. So that leads to deposition. So this is the golden rule that's like fundamental to all of this. If you only listen to, I mean, you're going to have to use this reference table, no doubt. But if you only listen to one like concept today, it's this one. Please, I beg of you. I promise it's going to come up over and over again. And it was demonstrated mathematically here that if water speeds up, we get erosion. Whereas if water slows down, it can't carry those particles anymore. It's got to drop them off. We get deposition. So there's our whole unit again. Weathering we've beat up on with all of those labs, talking about the way that rock breaks down into sediment. Now sediment is going to go through erosion and deposition based on the speed of the thing that is carrying it. As water goes faster and faster, it can carry more particles. It erodes them. It picks them up off the bottom of the stream or off the banks of the stream and carries them away. When it slows down, it drops them off. And yeah, all kinds of things can go into why does it speed up and slow down. So where specifically does this happen? What happens on river bends? What happens near the source? What happens near the mouth? Blah, 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 blah. There's a lot of like things that this applies to, but this is the rule that applies to all of them. This will save you on like all of those questions. That. Those two things. Okay. So let's think about rivers for a quick minute. Am I going way, way, way too long? A little long. Thanks for sticking with me. I do appreciate it. We've talked about watersheds. We've talked about the area of land that all drains into a stream. And high up in the watershed would be like the drainage divide along the tops of these hills. And the water then washes down into that watershed or drainage basin, into river systems, and then out towards the end um, into its what they call its base level, into the body of water it's flowing into. Let's note a couple things up here near the source. As a general rule, not a across the board 100% rule. Sorry about that. I know you hate that. As a general rule, up here near the source, the hills are going to be steepest. And then as you get lower and lower and lower in the drainage basin, where you're down where it's closer to the body of water that it flows into, is generally going to be like flatter. That's the general pattern on most drainage basins as they naturally occur here on Earth. So what this is going to mean then is that up here is going to be your fastest water. There it is already. With water speeding up and slowing down, what happens? Well, your fastest water is on your steepest hills. Also going to be your very straight streams. On a steep hill, water doesn't monkey around going left, right. It just goes straight down. It doesn't know what it's doing. It just gets yanked down by gravity. Whereas when it's flatter, in general, water slows down. And also what happens, I'd like you to circle this. This word right here is a vocab word that's going to come up a lot. Meanders. It's a fancy way of saying bends in a stream, but it's definitely one that we're going to want to get. Meanders or bends in the stream. What happens is that you get curvy, meandering streams. Okay, that's your broad general pattern. Not a guarantee that everyone's like that, but many are. So we'll do one last quick thing here, and then I'll show you where the classwork is. And again, I do appreciate this. I know this is going a little long. If we take a typical stream, and some break the rules depending on what like the mix of like available sediment versus bedrock is, but typical pattern here is that the broad area, the broad flat area where the stream might cut back and forth on, is called the floodplain. And now, especially where it's flat, you're going to start to get meanders. Again, if this were steep, the water's just going downhill. But where it's relatively flat, it meanders back and forth a little bit, makes all of these bends. So I want to really zoom in on one. Because what comes into play here is the direction. As this is flowing, it tends to be, if it's straight, fastest towards the middle. But as it's flowing, if it bends, it goes like hammering right into the outside of the curve here. That's where the fastest water is going to be. And then it heads back towards the middle and works its way down the stream. Over here, it goes that way, and then the fastest water goes hammering towards the outside of the curve. So you got to get left and right out of your head for these. It doesn't make any sense in this context because it's different if it curves one way. Sorry about that. Versus curving the other. The valuable thing to think about is it the outside of a curve or is it the inside of a curve? And A and D, in this case, are both the outside of the curve. And that's going to mean a couple of things. A, come back to this. That's going to be the big part. It's going to be the fastest water locally. And since you're all pros on this, if water speeds up, if it's going faster, what happens? Erosion. So the outside of curves is where erosion takes place. And since erosion is the movement of sediments, this is also going to be where it's deepest. That faster water picks up the sediment and moves it. That creates deep water. All right, what about B and C? Those are the inside of the curve. The fastest water goes whipping around all the way there, but it just kind of crawls to a nice slow pace right through here. So both locations B and C are both the inside of a curve. Again, don't think right left. This is going to be where locally we have the slowest water. And don't forget to come back to this critically important idea. If it's the slow water, what's happening there? Deposition. If deposition is taking place, sediment is dropping to the stream bottom, the water is going to be shallow. All right. I'm going to zoom way in. So what that means is through time, and this we won't look at in too hard a detail today, the outsides of curves get bigger and bigger and bigger and bigger because they're constantly eroding, whereas the insides of the curves get bigger and bigger and bigger because they're constantly depositing. So the stream itself, the bends will get larger and larger and larger and larger through time. And then if you can play that forward in your head for a minute, there's the outside of a curve, there's the outside of a curve. So eventually these two keep on eating away at the land until they meet. Then water takes the shortcut and it leaves behind this weird little body that we will come up with a name for, but not today because I think you guys have been through enough. Thank you very much for sticking through all that. Next, in the survival guide is a quick classwork, 10 questions. I had everybody in class like say, get right on it right now. It's only 10 questions, and they banged it out in like 5 minutes. So while you've got everything open, while it's fresh in your head, do that, and you are all set with lesson F. Thank you very much. So long for now.